Welcome back to PAA 607 Applied Data Analysis. This is week 8 of the fall 2018 online version of the course. I am, of course, Dr. Andy Crosby, your host for this broadcast, and I'm glad you joined us again this week. Okay, so we'll jump right into this week's material. We'll talk about some housekeeping items first. Then we'll jump into Lecture 8, which deals with chapters 9 and 10 in your textbook. The material that covers is the role of sampling in inferential statistics and hypothesis testing. This is another week where we're going to build a kind of a foundation for future weeks. And this material will be part of that foundation. Then we're going to talk about a summary and, of course, remind you of some upcoming materials. All right, so first, let's tackle the housekeeping. First item is that exam number 1 and homework number 4 scores are going to be posted within 1 week of the due date. So those items are both due on Tuesday, October 23rd. You will get your scores posted by Tuesday, end of the day on Tuesday, October 30th. Second item here is that homework number 5 is coming up due on Wednesday, October 31st. That's 1 extra day due to the YouTube outage we had. Normally our items would be due on Tuesday. In this case, it's Wednesday because we had a YouTube outage for posting the material. I also wanted to let you know journals number 2 are on the horizon. They are going to be due on Thursday, November 8th. In this case, you need 2 journals drawing from your choice of materials from weeks 5, 7, 8, and 9. This works very similar to journals part 1. Make sure you post and then make sure you comment on your colleague's post. You'll note here this is a Thursday due date. That gives you 2 extra days in this particular assignment due to the delay of some of the materials being posted on my end. So again, I want to make sure I'm fair to you, want to make sure I'm giving you enough time. So that's why we got a couple of delayed due dates here. If you have any questions, of course, feel free to just send me an email. I'm happy to clarify. Okay, so let's jump into the Lecture 8 material, which deals with the role of sampling in inferential statistics and hypothesis testing. I know it sounds like a mouthful, but it's really not that bad. Again, this is kind of a foundational week, and then we'll build on it in future weeks. So again, this deals with chapters 9 and 10 in your textbook. Now, I know you've seen the note on your screen before, but it's worth repeating again this week. We are not going to cover every single item or concept presented in the textbook, especially when we're getting into some of this material. Your textbook can read very much like a dictionary, and I understand that. So again, I'm going to highlight some important concepts in the lectures on homework problems and in study guides. You should definitely go ahead and read the textbook and read beyond your lectures even. The textbook has some nice examples of what we're doing in the lectures, but spend your time studying where the time is spent on lectures, homework, and the study guides. I'm not going to, pull some random material out of the textbook that we've never talked about in the course. So again, kind of focus your efforts on what we cover in class. Certainly read in the textbook, read the material that's related to what we're covering in the lectures, but you're not going to be responsible for every single word in the textbook. I realize very much this is like a dictionary. Okay, so part 1 here is the role of sampling in inferential statistics. So let's start out first with just an introduction to sampling. So one thing you might be wondering as you're watching this particular lecture might be, well, if we're interested in everyone, why don't we just study everyone? Well, as it turns out, that's often not possible. So to use the example we used in last week's lecture, we can't necessarily ask hundreds of millions of people across the United States what they think of the president's job performance. Although we're interested in everybody's opinion, we can't realistically ask every single person. So what we do instead is we sample. But even though we're using samples, we're still interested in the population. So in this case, we're interested in likely voters in the United States or registered voters in the United States. So, and you see this again on television. Among likely voters in the United States, X% of people approve of the president's job performance. So even though we're still using a sample to make that claim, we are still interested in the entire population. So now I want to introduce you to some terminology that is important as we start talking about sampling. So first, when we are referring to the population, that is everyone, descriptive measures are called parameters. So for example, if we want to refer to the percentage of all voters in the United States, every single voter in the United States who approves of the president's job performance, that is a parameter, the population parameter. They both start with P. Now, as we've talked about, we may not reasonably be able to get the entire population. We cannot necessarily ask every single voter in the United States reasonably. So what we do is we sample. And when we refer to the sample, descriptive measures are called statistics. Now again, both of these conveniently start with S, so sample, statistic. So just some terminology that you should know. So in addition to calling the population and the sample different things, so proportion and statistic respectively, we also write them a little bit differently mathematically. So both mean and standard deviation are written slightly different. We talked about earlier in the course that the population mean is written as mu, as you'll see on your screen here, just like the cat, mu. Population mean is mu. However, the sample mean is written as x bar, literally a letter X with a bar on top. Just a little bit different notation. Standard deviation, same way, we've got a little different notation. Population standard deviation, as we discussed earlier in the class, is written as lowercase sigma, as you see on your screen here. Whereas the sample standard deviation is written simply as S. So nothing crazy big here, just a little different way to refer to them in mathematical notation. Now, in addition to some changes in the way that we write population versus sample, we also have some changes in the way that we calculate measures for population versus sample. Now, first things first, calculating the sample mean is exactly the same as calculating the population mean. There's no change at all. All we do is we add up the numbers we have, and we divide that total by the number of numbers we have. Simple as that. It doesn't change at all. Now, calculating the sample standard deviation is slightly different. Now, I'm not going to go through the entire lecture on how to calculate standard deviation again. You've got that from earlier in the semester. And you're more than welcome to review that material if you'd like. So what I've done here on the bottom is to summarize the difference between population and sample calculations. And I'm going to explain it to you very briefly. So on the left, we have the population calculation, which we've been using throughout the semester so far. What you see there, on the top, we have a value, we subtract the mean, we square it, we sum up those squared values, we divide by how many values we've got, and we take the square root of that whole number. Now, the only thing that changes on the right is that we take our values, we subtract the mean, we square them, we sum it up, and in this case, we divide by n minus 1, the number of values we have minus 1, and then we take the square root of that whole number. It's the only thing that changes. Instead of dividing by n, we divide by n minus 1. That's the only difference. Simple as that. Now, you may be sitting at home and thinking, why, Dr. Crosby, why do we need to make that adjustment? Well, we do it to produce an unbiased estimate. Now, there's a bunch of math that proves this, and you're more than welcome to ask me. I'm happy to explain it. But for the purpose of this class, just know that we do this to get an unbiased estimate when we're talking about a sample. And I also don't want you to worry too much about the Stata calculation, because Stata has already been doing this since we started the class. It's already been using that n minus 1 denominator that we just talked about. It's been doing that for us since we started the class. And Stata does this because it's generally what we're dealing with as samples. So, for example, a sample of automobiles in 1978 that we've been talking about throughout the course. So this Stata already takes care of this for us. It's already using n minus 1. We don't need to make any changes there. So let's move on now to the topic of hypothesis testing. Now, again, this is an important topic to grasp because we're going to build on it in the weeks to come. So make sure you really understand this part of the lecture. So the first thing we're going to talk about when we're talking about hypothesis testing is, well, what are hypotheses exactly? Well, these are the tentative answers to research questions. More formally, we could say it's an expected but unconfirmed relationship between two or more variables. And we're going to get into this a little bit more in just a minute. Now, you might ask, well, how do I get hypotheses, Dr. Crosby? I don't go to Hypothesis Mart. Well, there are a couple of different ways you can get hypotheses. So, first one and the best one is to use theory to inform your hypotheses. Now, we teach that in a separate course here in the program. It's PAA 602, Organization Theory. So I'm not going to get into that too much in detail here, but theory is a great way to inform hypotheses. And you may have talked about this in other courses as well, is what is theory and why it's important. I'm not going to get into it too much here, but theory is a good way to inform your hypotheses. Second way you can get hypotheses is direct observation. And I've got an example here you may not be familiar with called Kids Food Basket. Well, so the idea here is Kids Food Basket is a nonprofit organization that happens to provide sack dinners for students that may not have food when they go home after school. And the idea here is that, well, we noticed that these students weren't doing very well academically, and we figured out, well, it could be because they're not eating. So we might have a hypothesis here that if kids get better nutrition when they go home, they may perform better academically. So this is a direct observation. We see something that's happening or not happening, and we wonder, well, maybe there's a relationship between, in this case, the variable of whether a child gets food or not and their academic performance. So that's direct observation. A third way to get hypotheses is, well, you could guess or some intuition. Now, be very careful with this. This on your screen here is actually a real quote from an academic paper that says, the author in this case says, "This was once revealed to me in a dream." Well, I wouldn't recommend you do this in an academic paper. Be very careful when you guess. Be very careful with your intuition. You want to back up a hypothesis with some reason why you would expect it to occur. Now, a little bit more about hypotheses. So an adequate hypothesis should speculate about the nature and form of a single relationship. So for example, an increase in education will result in a decrease in prejudice. For example, you do not want to include the kitchen sink. For example, an increase in education along with family socioeconomic status and an urban environment will result in a decrease in prejudice and an increase in the number of friends. This is too many things going on at once in one statement. You want to test the relationship between one thing and another thing. One single relationship. This is very important. So once you have a relationship that you would like to speculate about, how do you then write hypotheses? Well, you actually need to write two hypotheses kind of per relationship that you expect to be occurring. First thing you need to do is write a null hypothesis. This is the nothing hypothesis, a hypothesis that nothing has changed or happened. And we express this as H naught, H sub 0 there. So it's H naught. Then we need to come up with an alternative hypothesis. This is also known as the research hypothesis, depending on which textbook you read. Basically, the alternative hypothesis is opposite of the null hypothesis. And this is expressed as H sub A, for alternative, or sometimes H sub 1, depending again on which textbook you read. I'm going to use H sub A in this course because that's actually what's used in Stata. Now, so let's do some examples here. So for example, let's say that you have a research assistant. His name is Thurman Truck. Well, what an exciting name. So good old Thurman Truck is preparing a lengthy research report. So let's say we want to write hypotheses about this. Well, first we need to write a null hypothesis. This is the nothing happening hypothesis. Again, this is very important to remember. The null hypothesis is the nothing happening hypothesis. So in this case, Thurman Truck will not complete the research report. Will not. And then the alternative hypothesis is just the opposite of that. So Thurman Truck will complete the research report. It's as simple as that. The null hypothesis is the nothing happening hypothesis. Alternative hypothesis is the opposite of the null. So let's go ahead and do another example. So let's say we're wondering, for example, did arrests for prostitution increase in Prudeville, Oklahoma after a crackdown? So, just like the previous example, first thing we need to do is we need to write a null hypothesis, nothing happening hypothesis. So, in this case, following the Prudeville prostitution crackdown, mean prostitution arrests were not, nothing happening, greater than 3.4 per day, which happens to be the arrests that were happening before the crackdown. Our alternative hypothesis then is the opposite of the null. Following the Prudeville prostitution crackdown, mean prostitution arrests were greater than 3.4 per day. So again, you see it's just opposite of the null. The null hypothesis, something is not happening. Alternative hypothesis, something is happening. Now be careful. In this case, we're wondering, did arrests for prostitution increase? So clearly our alternative hypothesis is, well, mean prostitution arrests did increase. But that does not mean your null hypothesis should be that arrests decreased. You don't want to take the opposite direction. All you want to say is that they did not increase. The null hypothesis always needs to be something did not happen. And then the alternative needs to be something did happen. And this is one good reason why you'll often see the word not in a null hypothesis. So just watch out for that. Now, one note about null and alternative hypotheses, there are lots of different types of hypotheses. So for example, we might have a hypothesis about means. So the mean will or will not be a certain value. We might have a hypothesis about some causal mechanism. So for example, increased blood alcohol levels are related to slow response times. So when you're talking about hypotheses and you're reading about them, researchers don't always make explicit references to the null hypothesis when they're testing relationships or when you're reading a paper. However, it is absolutely central to the logic of significance testing, which we're going to cover later on in the course. And it's always implicit. There's always a null hypothesis there, even if the author didn't write it. So let's do an example. So let's start with talking about means, which is something we know how to calculate. Let's say that the national mean score for SAT math scores is 500. And you want to know if California students are different. So your null hypothesis then is that the mean SAT math score of first-year California college students is not greater than 500. So again, something is not happening. Our alternative hypothesis then is that the mean SAT math score of first-year California college students is greater than 500. So, great, we've written a null hypothesis, we've written an alternative hypothesis. Great. So now what do we do? Well, one thing that we could do is we could sample. So, happens to be that there are 160,000 college students in California, which is too big to ask everyone, at least reasonably. So this is where a sample comes in. So what we could do is we could randomly select 1,600 students from this population, just a small subset. And let's say we calculate a mean SAT math score for California students of 505 and a standard deviation of 2.5 from that sample. Well, we already know how to calculate a mean score for a sample, and we know how to calculate a standard deviation for a sample. We also know that Stata can do both of those things for us. So then what we want to know maybe is, well, are California students different than 500? Or is this just a random chance that we happen to have a little bit higher score here? So to answer this question, we return to this picture that we saw in previous lecture that talks about normal distribution in the bell curve. And we talked about previously that 95% of our data, if they're normally distributed, live between minus 2 z-scores and plus 2 z-scores, minus 2 standard deviations and plus 2 standard deviations. Well, what does that mean? Well, what it means is that the data outside of that zone is pretty lonely, as I've now put on your screen here in yellow. The data that are less than negative 2 z-scores and more than positive 2 z-scores, those are pretty lonely data, not a lot of data out there. So this is how we start to answer the question, well, are those California students unique? So as it turns out, what we can do is we can graph our data. We know, in this case, that our national mean is 500. And we know what the standard deviation is because we were told that. From that, we can figure out, we can make a graph here, and we can figure out that indeed 505 is 2 standard deviations above the national mean. And I've shaded it here on the graph in front of you. Actually, your textbook author shaded it for me, but it's shaded nonetheless in the graph in front of you. So since 95% of our data, as we talked about, is within that zone of plus or minus 2 standard deviations, a mean of 505 is unlikely to be by chance because we're way over on the right there. We're outside of that zone where 95% of our data live. So it's unlikely to be by chance. Now you might wonder, well, how unlikely? Well, this is where our statistical test starts to come in. But before we get to statistical tests, we need to talk about something called the empirical rule. So we said last week that 95% of our data are between plus and minus 2 standard deviations from the mean. There's more to that claim, and it's called the empirical rule. Your textbook doesn't explicitly call it the empirical rule, and a number of textbooks don't. But it does tell you in Chapter 10 the basic components of the rule. And some textbooks also call this the 68, 95, 99.7 rule for reasons I'm going to tell you in just a minute. So the empirical rule. So let's talk about that. So the empirical rule says that when data are approximately normally distributed, which is what we talked about last time, what this means is 68% of our data lives between plus and minus 1 standard deviation of the mean. 95% of our data falls between plus and minus 2 standard deviations of the mean. And that's what we mentioned last week. 99.7% of our data falls between plus and minus 3 standard deviations of the mean. So this is basically just an expansion of what we talked about last week. So we talked about last week, 95% of our data is between that plus or minus 2 standard deviations. The empirical rule is just expanding on that. So now we're talking about we've got 68% of the data between plus and minus 1 standard deviation, 95% between plus and minus 2 standard deviations, and 99.7% of the data between plus and minus 3 standard deviations. So all we're doing is expanding on what we talked about last week. So let's return to our data for a moment to try and answer that question. Exactly how unusual would that mean score of 505 from the California students be? Well, we already know that a mean of 505 is plus 2 standard deviations from the national mean. So that's already kind of far out. We also know that 95% of our data lives between minus 2 standard deviations and plus 2 standard deviations. So that means the high values, the values of 505 and above, there's only a 2.5% chance that we would be over there. Now you might say, well, why 2.5%? As it turns out, 95% of the data are between minus 2 standard deviations and plus 2 standard deviations. That means 5% of the data are outside of that. Half of those 5% are on the high side, half of them are on the low side. So we're interested in this case on the high side. We've got a mean that's kind of high. Only a 2.5% probability that that would occur by chance. So again, how did we figure out that out? Well, let me show you graphically. So doing a quick retro rewind from week 7, we still know 95% of our data live between minus 2 standard deviations, and plus 2 standard deviations, which means that 5% of our data are outside that. 2.5% of those data are on the low side. 2.5% are on the high side because it's equal on both sides. That's where we're getting the 2.5%. So it's the high side in this case. We're looking at that mean score that's above what we expect. So we're returning to our data just one more time. So we know a mean of 505 is plus 2 standard deviations from the national mean. That would mean that there would only be roughly, now your book has an exact calculation. It's not technically plus or minus exactly 2 standard deviations, but we're kind of rounding here. And for the purposes of this class, this is all we really need. So there's roughly a 2.5% probability, 5% divided by 2, that this would occur by chance. So this means that we now have what's called a p-value of 0.025. And I'm going to explain what p-values mean in a moment. But basically, this is saying we're now converting that percentage, that 2.5% probability, into a decimal, 0.025, and that is what's called a p-value. And Stata will normally provide this. We're going to discuss this more next week. But just know that we're basically converting this probability number into a decimal now, and that's called a p-value. So let's talk a little bit more about p-values. Now you may be sitting at home and thinking, Dr. Crosby, what exactly is a p-value anyway? Don't worry, I'm here to help. So a p-value indicates how unusual our values are compared to the null hypothesis. And in social science, and public administration is a social science, p is less than 0.05 is a common threshold for what we call statistical significance. And what that's basically saying is if we see a p-value of less than 0.05, that means we can look at that value and say, yeah, that's a really unusual value. Now, some fields like aerospace use 0.01 as a threshold for statistical significance. But in general, social sciences, and again, public administration is a social science, use this 0.05 as a common threshold for statistical significance, which means, again, if we see a value of less than 0.05, we can point at that and say, yeah, that's a really unusual value. Now, when we're talking about threshold for statistical significance, this is also known as alpha. So alpha is basically saying this is we need to see values below this particular level, in this case 0.05. If we see values below this, we consider that statistically significant. If we see values equal or greater than this, they're not. So, if we see a p-value of exactly 0.05, that would mean that we have a 5% chance of our value occurring by chance. And if we saw a p-value of 0.01, that would mean we have a 1% chance of our value occurring by chance, just to give you an example of what exactly these p-values mean. So as you might have concluded by this point, the smaller the p-value, the stronger the evidence is against our null hypothesis. So if we have a p-value of 0.05, that means there's a 5% chance that our value occurred by chance. So in our SAT example, that means there's a 5% chance that a mean value of 505 would be by chance. But there's a 95% chance that it was not chance at all, that these students really are statistically significantly different. If we had an even smaller p-value than 0.05, that would mean we're even more sure that these students really are different and it's not just chance. So the smaller the p-value, the stronger the evidence is against your null hypothesis. So again, we can look at this visually, and again, those values all the way over to the right on your graph that's normally distributed, or all the way over to the left, those are the values that have what are called low p-values. So you see here the shaded value all the way over to the right-hand side of the graph, that would have a very low p-value because there's a very low probability that you'd be in that area by chance. And we can interpret various p-values in the same kind of manner that we did our p is 0.05. So, for example, if we have a p-value of 0.1, that would mean there's a 10% chance that the value we are seeing, for example, a mean SAT score, would happen by chance. That's a pretty weak claim when you think about it. If you're saying there's a 10% chance that your claim is just by random chance. So that's why we don't want to use p-values that high as a threshold for significance. Then we see what we already talked about, 0.05. That would mean there's a 5% chance that the value that we're seeing, for example, the SAT mean score, is occurring by chance. Again, this is a standard in social science. That's the standard threshold. We were looking for p-values less than 0.05 to say, yes, that's a really unusual value. And then if we go to p is equal to 0.01, that would mean there's a 1% chance that the value that we're seeing would happen by chance. And again, lower values equal stronger evidence. If we only have a 1% chance that the value we're seeing is occurring by chance, that's really strong evidence. There's almost no chance that it would happen just randomly. So then, once we've collected our data relevant to the hypotheses, and again, we're going to go through the actual statistical test for this in coming weeks. So I don't want you to worry too much. I just wanted to introduce you to the concept of p-values. But once we've collected our data relevant to the hypotheses, we can evaluate them. And when we do that, we either do not reject or we reject the null hypothesis. One note here, please do not say that you accept the null hypothesis. We either do not reject it or we reject it. Make sure you do this. So if, for example, way back in our Thurman Truck example, if Thurman Truck will not finish his report by August, we do not reject the null hypothesis. So let's return to our SAT score data just one more time to talk about statistical significance and then how that relates to our hypotheses. So in this case, we said there is a very small chance, only about 2.5% chance, which translates into a p-value of less than 0.05, that a mean SAT math score of 505 or higher would occur by chance. And as such, we would reject the null hypothesis in favor of the alternative hypothesis. We would do this because if you remember right, our null hypothesis was that the mean math SAT score is not greater than 500. We see that there is statistically significant evidence that that is not the case. So we are rejecting the null hypothesis in favor of the alternative hypothesis. Now, all of this said, sometimes we can be wrong. So let's talk about error a little bit. So when we're testing null hypothesis, we can potentially make two different types of errors. The first type of error is known as a type 1 error. And what this is you reject the null hypothesis, even though, as it turns out, the null hypothesis is true. So we don't want to do that, but that's what's known as a type 1 error. Type 2 error is that you accepted the null hypothesis when in fact it is false. So again, you don't want to do that either, but that's known as a type 2 error. So there are errors. We can come to the wrong statistical conclusion, and one of these two types of errors can occur. So I want to give you a little prelude to next week as well. So next week we're going to talk about something called t-tests. T-tests, what we're doing there is we're statistically testing the differences of means using stata. So if we want to statistically test whether the mean math SAT score is greater than 500, we can run that test in stata, and we'll get a p-value just like we talked about tonight. So the p-values in a t-test are automatically provided by stata. But the reason I introduced them to you tonight is that you need to know how to interpret p-values for the rest of this course. So make sure you understand what a p-value is before you jump into next week's lecture and the week after that. All the work we're going to do from this point forward will involve p-values. So make sure you understand what a p-value is. Make sure it's critical to know this. So even though we're not using stata this week to test it, we will be next week, and we're going to use p-values for the rest of the semester. So please make sure you know this. All right, so let's sum things up. So one thing I'd like you to do is to know the difference between a population and a sample, and know that there's a slight change in standard deviation calculation, not a lot. I'd like you to know the difference between null and alternative hypotheses and how to write them. You're going to get some practice during your homework. I'd like you to know what type 1 and type 2 errors are. I'd like you to know the empirical rule, the 68, 95, 99.7 rule. And I would like you to know p-values and how to interpret them. Again, I cannot stress this enough. Knowing p-values is critical for the coming week. So please make sure you understand this. All right, so upcoming material and due dates. October 31st, Wednesday, homework number 5 is due. That's one extra day due to the YouTube outage. Thursday, November 8th, homework number 6 is due, and journals part 2 are due. I'm giving you 2 extra days on both of those because of the delay in the lecture materials. And then next week, we're going to talk about testing the difference between groups and t-tests. We're also going to lay the groundwork for ANOVA next week. So please, I cannot say this enough, please make sure you understand p-values because we're going to use them a lot from this point forward. And as always, if you have any questions, please feel free to send me an email, acrosby@pace.edu, or give me a call. I'm always happy to help. Thanks very much and have a great week.